Before we begin, this picture has been uploaded to Google Classroom, so please check that, download it, keep it on your desktop for studying. It'd be very helpful. Now, on to the notes. We are now talking about hearing, the sense of hearing, and we're going to be using receptors that we call mechanoreceptors. If you recall, mechanoreceptors are your touch receptors, pressure receptors, not sound. We don't actually have sound receptors, so we need special parts, which is why this is a special sense. We need these special parts to help convert pressure into sound. And all of this takes place in your ear. And your ear is not just this part hanging on the side of your head like people think it is. No, this is just a part of your ear. Your ear continues into your head all the way to your brain, if you count the nerve going to your brain. And we are going to separate your ear into three sections. We call the external ear, the middle ear, and the inner ear. I'm sure you've heard of an inner ear infection. That's kind of a big deal. So what we got here is the picture I actually drew on the board. That's what I was looking at before. And your external ear is made up of the part that you are aware of, that you're used to seeing, is actually called the auricle. Sounds kind of like oracle, right? You guys know what the oracle is? Greek mythology. The oracle was a woman who could hear the voice of the gods. So this is pronounced auricle, but it's the same idea because this is what is collecting the voices, helps you hear things. And is actually going to funnel the vibrations of sound into your ear canal, which we are now calling the external auditory canal, or the external auditory meatus, which is the fancier science word that I'm going to give you, external auditory meatus. At the very end of your ear canal is your middle ear, made up of your eardrum and these three bones. What's important here, I'll talk about in detail later, is the eardrum is big, and then smaller bone, even smaller bone, much smaller bone. So it goes from big to small. And that's going to help amplify sound. Yeah, it actually makes things louder to you. Physics is weird. And as this is vibrating, all of these are vibrating, which is pushing up against your inner ear in this all-important organ we call the labyrinth. We call it the labyrinth because it's a maze of tubes. And as this is getting all the vibrations, you have an auditory nerve that is going to pick up that information and send it to your brain. There it is, guys. That's the entire ear in a nutshell. Yeah, that was a nutshell. Let's go into detail. Auricle, part on the outside that you're used to seeing. Again, that's pronounced auricle. Weird pronounce. This is the part on the outside that collects sound waves. Nice and simple. It's a funnel. And as it funnels those sound waves in to your external auditory meatus, which is just a tunnel, is going to carry sound waves to your eardrum. All right, in your middle ear, we are starting off with your eardrum, or what's actually called the tympanic membrane. This tympanic membrane is just a drum. In fact, most people would just call it the eardrum, even doctors. So I would suggest memorizing that word. In fact, that's the word I'm going to put on the test, eardrum. Memorize that one. It is a cone-shaped membrane, and it's going to vibrate with the sound waves. So again, as the sound waves come in, sound is pressure. So as the pressure waves come in, they put pressure on the eardrum, making it vibrate. After that are those three bones. We call those three bones the auditory ossicles. The auditory ossicles, these three bones in the middle ear, it's going to transfer the vibrations from the eardrum to the labyrinth. The malleus is attached to the eardrum. The incus, slightly smaller, attached to the malleus and the stapes, and then the stapes attaches to the labyrinth. And again, I said it gets smaller in each step. This is a weird thing about physics, guys. Rule: you cannot destroy energy. And this pressure is an energy. Your pressure wave is energy. So this energy is taking up this much space. So by the time it gets transferred here, you can't lose it. You can't get rid of it. So it's all jammed in this one small spot. That's a lot of energy being condensed, which means it's a lot of energy hitting this one spot, which means you're actually hitting this labyrinth way harder than you would have if it was just the eardrum. And all of that energy gets put into the little stapes, which means all of that energy is hitting this one little spot. So this guy feels like it's getting hit harder. I'm going to fast forward a bit. This whole labyrinth, I want to focus on just this circular part. That's called the cochlea, and that's what the sound's going to be coming from. So I'm going to unravel it because that makes life a bit easier.
There are actually 3 chambers inside, but let's take a look at the central part. The stapes is causing pressure waves to travel through the structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, they encounter fibers with the correct resonant frequency and energy is released.
What he just said was kind of complicated, so it was kind of a weird way of saying it. Let me reword it. Different vibrations will affect fibers in different ways. Different wavelengths and different frequencies will vibrate different parts of these fibers. So you're actually creating a pattern. And what he's about to say is now the different parts vibrating will affect these little hairs, and that's what sends a signal. Remember I said different vibrations make different patterns, and that's what he's going to show you.
Right. And to do that, I have to put 2 fingers there and bow it in this position.
And that vibration affected the plate in certain ways to create patterns in the sand. Same
there.
Plate, but he created a different vibration, so he got a different pattern. So different vibrations make different patterns, which affect your cochlea in different ways, and then it tells your brain different information, so that your brain tells you that you hear different sounds. And then, of course, we can have some fun with that. So, as you see different patterns, you're also hearing different sounds. And that is how your ear works. Different vibrations, different frequencies vibrate different patterns in your cochlea of your labyrinth, and your brain interprets different sounds out of it. And the bones are going to amplify those vibrations so that your cochlea really gets it. So that inner ear part is called the labyrinth. It starts off on the top with these 3 semicircular canals on top of this bulb, which I will go into detail about later. But they have to do with balance and equilibrium. That's what keeps you from falling over. So I'm going to come back to that. I want to focus right now on the sound part. Down here, the circular part that I just showed you in that video is the cochlea. That is where all those fibers are that are getting vibrated. So that's what we are going to use for hearing. It contains what we call the organ of Corti, which is, all of the fibers. I'm not going to make you memorize organ of Corti. I'm going to test you on calling the whole thing the cochlea. So that's the word you need to know right here. And then once all that information is set in the cochlea, you have what's called an auditory nerve. In the picture I gave you on Google Classroom, I have it listed as the cochlear nerve. Same thing. The nerve in the cochlea. Cochlear nerve is a type of auditory nerve. It connects to the cochlea and carries the information to the temporal lobe. That's right, guys, temporal lobe. This is a mechanoreceptor. I said that in the beginning of this lesson. We already know mechanoreceptors typically send information to your parietal lobe, telling you what you feel. But this is going to your temporal lobe instead, telling you something else. The temporal lobe will process the information differently and tell you that those vibrations are sound. Different part of your brain gives you different information. All right, so again, auricle, external auditory meatus, eardrum, the 3 auditory ossicles, labyrinth, nerve, right? So take a look, follow the pattern. The sound waves get collected. That's what the dots are, pressure waves. They start vibrating the eardrum, which causes the bones to oscillate, which is the name of that motion, and sends the vibration into the labyrinth. Then the shaking labyrinth shakes in very specific ways based on the frequency of this original sound wave. Different frequencies here means different shaking here, which means different information being sent to your brain. And then your brain interprets all that information as different sounds. So that's what's important, guys. Different vibrations originally out here get interpreted differently here. Anyway, I did say I was going to cover equilibrium really quick. I don't need to spend too much time on it because today was mostly about sound. But we got organs of dynamic equilibrium. This I covered it in detail in the vocab. And down here, organ of static equilibrium. The dynamic equilibrium are these three semicircles. And notice that they are in three different directions because you have one that handles up and down, one handles forward and backward, and one that handles left and right. So three different directions, or dimensions we call it. So as you're moving your head around, there's water inside sloshing around up against nerves. And as that water sloshes around in different directions, the nerves send messages to your brain. Your brain performs math that you didn't even know that you knew and tells you which way is up and down no matter how much you're spinning around. And then down here beneath that, this bulb, it's called the central bulb, is just water standing still. So if you're not moving around, you're just going to stay perfectly still, that water, gravity pulls it down, and a nerve in there knows which way is down when you're not moving. So the loops handle when you're moving around, and the bulb handles balance when you're not moving around. And then the cochlea is for sound.
People, I have a story for you about equilibrium in that inner ear. In that those tube-like canals, etc., somewhere in that bulb area, there are crystals. And the crystals are fixed. They stay inside your inner ear in a spot. And they help with your equilibrium. Well, last April, I had a virus that attacked my inner ear. And what happened is it loosened the crystals. And I got something called vertigo. And vertigo is a symptom. What happened was on a Sunday morning, I woke up just out of bed and the room started spinning. And it kept spinning and it kept spinning. I tried to get up and I had no balance. I tried to keep my head still, but I still had no balance. When I leaned over to put my shoes on, I had no balance. I was dizzy and it was constant. It was just like almost like a freeze frame. Like it would just keep going. The room would keep going and going and going. It was first I saw it on the TV. So what I had to do is very slowly, I tried to keep my head still and I moved down the stairs to my living room and I called 911 because the room would not stop spinning. I thought it was the coronavirus and I had symptoms of it, but it was not, okay? I got into and what happens with vertigo, you lose your balance, you totally lose your balance, and with the room spinning, sometimes you get nauseous and you can get sick and throw up. Because think about the room just constantly spinning and you can't stop it. So I end up going into 911 and then they diagnosed me with a vertigo. It was a virus that attacked my inner ear and upset this equilibrium part that Mr. Coney just explained. There's these crystals, and instead of them being in one spot, they were floating around. So just a little bulb in that inner ear can affect your whole body.
Speaking of dizziness, there is something else I wanted to show you guys. So there's a good segue there too. Now, what Mr. Mossack was just talking about was a structural problem with crystals floating around. Well, you can also get dizzy without that too. The more common one, the one little kids like to do by spinning around. I want to show you guys a little physics thing here. Remember, it's all about liquid in that organ, right? So yeah, I got my cup of coffee, and I'm not tricking you. There's actual coffee in there. I'll make my camera. See, you can see coffee floating around, right? And no magic trick, you still see it here. I can put this upside down without spilling it. In fact, I'm going to do this toward my computer. That's it. That's how confident I am in this. Ready? So, nothing, right? So why? And look, it's just still Still coffee in here. Still see it. All right. So why is that happening? Why am I able to, camera? Why am I able to spin my coffee around without it spilling out? Because physics, as it's going with momentum, the liquid is going to the bottom of the cup and it's staying at the bottom of the cup. Well, it's the same thing with your those three semicircular loops, right? They need moving liquid to tell your brain which way is up and which way is down. But if you start spinning around, then the liquid gets pushed to the walls and stops moving, and now your brain doesn't know which way is up and which way is down, and it doesn't know what to tell. Your brain doesn't know what's going on anymore. I'm not acting, by the way. Whew. Oh, God. That was a dumb idea. Oh, I need to sit down. All right. All right, so that's it for the notes. So you guys are free to go. You can have a great day, and I will see you in class tomorrow.